Hope everyone's doing well out there. So this video, I wanted to go over a little bit more with carbon. I'm going to do a little bit of enzymes, talk about those a little bit more, just like I told you I was going to in the last video. So let me draw my enzyme here, and we'll label the parts just like we did last time. So, okay, there's my enzyme. Now remember, enzymes, they are proteins. And these proteins are made up of the monomer amino acids. So we could say it's made up of amino acids. Good. Now, what is going to bind into our enzyme is called the substrate. Substrate might be a chemical, might be a certain type of food, whatever, okay? Now, if you notice, the substrate I have fits this area right here on the enzyme called the active site. Let's say I bring in another substrate. The substrate looks like this. That, whatever that is right there, that little spike, is not going to fit perfectly in there. If that is the case, the enzyme doesn't work for that substrate. Enzymes are very specific on the substrates that they work upon, okay? So this substrate fits real nicely into the enzyme. If it doesn't fit nicely, enzyme doesn't work for it. Our goal is for the enzyme to take that substrate, bring it into the enzyme. Enzymes are going to do some work on it, and then afterwards, we are going to have the enzyme converting that substrate into products. So in other words, decomposing them into something smaller. Okay? All right. So let me go over this graph here, and then we're going to come back. I'll erase the graph, and we'll do a little bit more with this because there is some variation in the enzyme there. All right? Now, let's say normal day, okay? You are going through your normal processes in your body, and here's what happens. Okay. So over here, these are our reactants. All right. We can also call that our substrate. Over here is where our products are. That is after the decomposition of the substrate has already occurred, all right? Right here, in this whole mess here, from here to here, that is called the activation energy. This activation energy, that is the energy needed in order for this reaction, for the reactants to be converted into the products. Think of it this way. It's like a hill, right? You are on your bicycle going up the hill. If you only get to here, guess what? You are not going to be riding down that hill, okay? You have to make it all the way to here so that you can go down the hill. If you only make it to there, or if you only have that much energy, tough, right? We ain't getting there. So we got to make it, or we got to have enough energy to get to the top of the hill, okay? Now, on this graph, guys, I got my y-axis labeled, my dependent variable. I got my x-axis labeled, my independent variable. I didn't really put many, numbers in here. So let me do that real quick. All right, we're not going to be perfect here. We'll say this is 20, so 10, 20, 30, 40, 60, 80, 100, and there's 110, okay? So how we would calculate the activation energy for this is going to be the top of the hill, so I would say that's about 100 joules. I'd say it's about 100, okay? To the reactants. So I'd say that's about, here's 50, here's 40, maybe about 45. So it would take us 55 joules of energy so that this reaction can occur. Okay? Now, like I said, normal day, okay, you're feeling kind of all right. Now, you didn't realize it at the time, but right then when this was going on, you were sick, okay? Maybe it didn't hit you hard yet, but it will, right? What actually happens when you were sick and you got a fever or something, your body is not functioning the way it normally does. In other words, why it's not functioning properly is actually your enzymes are not working properly. Okay? They're actually not working at all. So, like I said, you're starting to get sick with the green line. Let me draw you another line of what would happen if these enzymes were working perfectly. So I'm going to follow my green line. It's going to be the same thing at first. We're going up the hill. And we're going to end at the same area. Okay? Look at the difference there. Here, I was all the way at 100. Here, the top of my hill, maybe about 65. So our activation energy of the red guy here, we're still at 45 starting, but we're only going up to 65. So that means we only need 20 joules of energy for this reaction to occur. We still get to our products. We still get to where we need to be, okay? But it requires us a lot less energy. So instead of using 55 joules of energy, we're only using 20 joules of energy. Why is that good for us? Well, you have more time to go play soccer, play sports, cheerlead, whatever, okay? You have more energy when your enzymes are working to do things that you like to do. So the red line here, the red line is when an enzyme is working or an enzyme is present. The green line up there, the green line is when you're sick and your enzymes are not working properly. Or we could just say enzyme is absent. Okay? They usually like to put these graphs on the Keystone, guys, so make sure you know about the activation energy and the enzyme stuff. Whatever hill is lower, okay, that's going to be the one where your enzyme is present. Big hill, enzyme is absent. All right? Okay, so let me explain, because right now, guys, you're like, bro, like, I want to use the red hill every single time. Why the heck would my body take the green hill? It wouldn't make any sense, right? Why would my body use more energy if it doesn't need to? Get them enzymes working, right? Let me explain. So in order for our substrate or reactants to be converted into products, it's got to bind into that active site. Now, your normal body is 98.6 degrees. Okay? Let's say with that enzyme, guys, we are going to change your body temperature to a nice, lovely, balmy 102 degrees Fahrenheit. Oh my goodness. Not good, right? Let me show you what happens to the enzyme. Oh, looking good, looking good. Everything looks normal, and then brrr. We no longer have that nice active site. Guess what? No active site, no bonding. If you cannot bind the substrate into that active site, we don't get our products. That means we got to take in that graph the green hill if our enzymes aren't working. What we call this is a denatured enzyme. That enzyme has lost its active site. Okay? So, that's a denatured enzyme. All right. Now, enzymes are very, very specific at what temperature and what pH they are going to work at. Okay? Now, you guys have different enzymes in your body. you have tons of different enzymes. There's enzymes, like I said earlier, there's enzymes in your saliva, there's enzymes in your stomach, there's enzymes in your intestines, okay? Your mouth might be slightly acidic, but it's gonna be around a 7, somewhere around there for pH, so it's fairly neutral. Your stomach is gonna be at a 2. So I'm just gonna draw 3 enzymes here, okay? We're gonna say this is a stomach enzyme. It wants to function at a pH of 2. Let's do an enzyme in your small intestine. Your small intestine probably is going to have a pH of around 11. And then your saliva, or in your mouth, maybe a 6, maybe a 7, somewhere around there, okay? All different enzymes. So your stomach enzyme is going to function naturally in a pH of 2, function naturally in a very, very acidic environment. Small intestine likes the basic environment, okay? Saliva, yeah, those enzymes, they're called amylase, is the enzyme in your saliva. It functions pretty well at a 7. Okay, let me do one more graph with you. So, in our second graph, and I'm going to go quick on this one. So let's call this the function of the pepsin enzyme. Pepsin is the enzyme that is in your stomach, so it's naturally at a pH of 2. Down here, I'm going to do my pH. Here's going to be 0. We're going to say this is 2, 4, 6, 8, 10, 12, and then our highest is going to be 14, okay? Over here, we're going to write enzyme activity. Again, I said pepsin is going to be in your stomach, okay? Stomach has a pH of 2. So, enzyme activity, let's draw what it would look like. Around 0, it's going to have a good bit. Around 2, it's going to have a whole lot, because that's perfect. And then it's going to drop, 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 drop. And then when we get to basic here, or go to the weak side of acids, it's going to become pretty much 0. Okay? So 2, pH of 2, is the optimal pH for pepsin function. Okay? If you take that enzyme pepsin and you put it inside of the small intestine that's around 11 here, guess what? That function is going to be 0, because at this area right here, that enzyme is now denatured. Okay? The enzyme is now denatured. It's not going to work. But the nice thing is about enzymes, guys, it's in a pH of 11 here in the small intestine. It's like, oh crap, I don't want to be here. If it goes back to the stomach, it's not going to die. It's fine. It's going to go back to the stomach and it's going to be like, hey, I'm at home. Let me start working again. I can do my job again. Okay? So enzymes, they can keep getting reused over and over and over again, and they can go from being denatured back to being renatured again. In other words, back to functioning normally. Okay, last thing I want to go over with you guys today, and I told you I was going to do this in the last video whenever I was going over the macromolecules with you, is carbon. Now, every single one of our macromolecules is made out of carbon. So, let me draw some carbon chains for you guys here. Okay. When we are drawing carbon chains, we can make something called a hydrocarbon. Now, for carbon, carbon is always going to form 4 covalent bonds with other molecules here. So what you want to do is you want to, let me label these carbons. This will be carbon 1, 2, 3, 4, and 5, just so you know what one I am talking about. So look at carbon 1 here. How many bonds does it have coming out of it? So if we look at carbon 1, it only has 1 bond coming out of it. What we got to do is we got to make sure that that carbon has 4 bonds coming out of it. Well, if it has 1, I need 3 more to get to 4, because 1 plus 3 equals 4. Wow, that's hard math right there. But you want to add 1, 2, 3 bonds to it. What do we put on there? I told you guys we were going to make a hydrocarbon. Hydrocarbon is simply hydrogen and carbon, and that's it. So I would add some hydrogens. 1, 2, 3 hydrogens. Okay, done with carbon 1. Let's look at carbon 2. Carbon 2 has 2 bonds coming out of it. So I got to add 2 more, just like that. Look at carbon 3. Carbon 3 has 1, 2, 3 coming out of it. So I got to get to 4. I only need 1. There you go. Carbon 4, once again, 1, 2, 3 coming out of it. I'll put this one down here. You can. It doesn't matter where you put it, as long as you got 4. And then carbon number 5 has 1 coming out of it, so let's put some 3 in there. Okay. Moral of the story, guys, we always need to have 4 bonds coming out of each one of our carbons. Okay. All right. Hopefully this helped you with enzyme activity, and then going over the main element, carbon, that's going to make up our macromolecules. See you guys next time. We'll go over water. Have a good rest of your day.